This video is about convective weather forecasting. So we are talking about the thunderstorms and the related phenomena. First of all, there are a lot of indices available for you to use that should help you to forecast convection, but those indices are generally not good. So it's best not to use them, basically at all. They are always lacking one component of ingredients needed to produce convection. Basically, there are 3 ingredients that we need to produce convection. So first of all, we need to have instability. And in my view macro, the instability is noted as a lapse rate. So this green over here. Then we need to have moisture, especially on the lower levels. And here I have the lowest 500 meters mixing ratio. Then I need to have lift. So something that pushes these particles higher up in the atmosphere and initiates the convection. And here I have 850 hectopascal temperature as well as geopotential height. So this is a way for me to find frontal boundaries since we live on the mid-latitudes. So when it comes to lift, you always need to have something in a mesoscale that is lifting the parcels higher up in the atmosphere. So it could be a boundary, topography, or just hitting off the ground, especially in the tropics. And on my 4th row, I have shear. Shear is not considered as one of the main ingredients of the convection, but it is helping a lot. Especially if we want to have some severe convection that is organizing into MCS or squall line or anything like that. Then you need to have proper amount of wind shear as well. Then on the other side, I have CAPE. So CAPE stands for convectively available potential energy. And it is a good value, but since it only combines the 2 ingredients, so the instability and the moisture, you still need to look for the source of the lift anyway. And if you have a large amount of CAPE, you don't know whether it's due to the moisture content or the deep lapse rates, and in which ratio. This is the reason why you still need to consider all the other ingredients as well, and I really prefer if you would do it like this, on a map where you have all the different ingredients and you can see them separately. This way you can try to find the hot spot where all of these ingredients are coming together. So here I have an example where all the ingredients are coming together. Especially in the mid-latitudes, if our lapse rates are above 5.5 or preferably closer to 6 or 6.5 Celsius degrees per 1 kilometer, that's deep enough. So I can see that there is this band of high lapse rates, which is good. Then from the moisture content, I can see that this area is also having large values of moisture as well. So they are above 10, which is generally enough, but closer to 12 or even 14 you go, the better it is. So here I have around 14 grams per kilogram. I can clearly see that there is cold front approaching. So we can also find the source of lift. So even though this low pressure system with its fronts is considered as synoptic scale system, individual fronts are still a mesoscale features. So this lift operates in mesoscale, which is important for us because only mesoscale lift is enough to push the parcels upwards. Synoptic scale lift operates in centimeters per second scale, whereas mesoscale lift is operating in meters per second scale. And we can actually see that we have very high shear values here as well. So shear operates as a cherry on top of a cake, and we seem to have that ingredient there as well. We can see that our CAPE is very high, so values of almost 2000 joules per kilogram if we're considering most unstable CAPE. So that is a large value. But we still need to look at the sounding. So just comparing the ingredients isn't enough. The sounding is basically telling you the truth of how these ingredients are operating in vertical scale. So if I take my sounding from here, I can see that it's clearly a convective cloud. So the most unstable cape, which is indicated as this green line here, is on right side of this temperature curve. So we have positive cape, and we also have a little bit of negative cape here at the bottom, which is called SIN, so convective inhibition. On the right side, we can see some indices. So we have different partial methods. We have surface-based method, mixed layer-based method, and most unstable-based method. And if we look at the most unstable cape, it says in this point 1251 joules per kilogram. SIN is also quite large, it's -45 joules per kilogram. So that's why we need the source of lift, because we need something to bring the particles from the ground through this negatively buoyant layer so that the particles can freely rise from this LFC level of free convection. When you are considering convection, there is also an option called photograph available on SmartMet. And this is a great tool when you are trying to forecast the convective mode, for example. So whether it's going to be single cell convection, multi-cell convection, or even supercell convection. So we are not going to go into details of this photograph and how you read it, but just the overall idea is that you have shear represented in this kind of graph. So these are meters per second in all directions, and you also have 1K, 3K, and so on. These are kilometers, so 1 kilometer, 3 kilometers, and 6 kilometers. L and R stands for left mover and right mover. These are related into supercell convection. And M stands for mean flow. So what you are supposed to look from here is the curve and how it looks like, and whether you have enough wind shear or not. So if you're just staring at the wind barbs, it's very hard to see the directional or even the velocity shear. That's why this graph is separating these components quite nicely, actually. Next, we can go through what we can actually see from the sounding. So what are typical rule of thumbs that we need for some convective phenomenon to happen? So let's start with lightning. For lightning, you really don't need much. You need a little bit of cape, a little bit above 100 joules per kilogram should be enough. But you need to have that amount in the right temperature zone. So usually the rule of thumb goes that when your equilibrium level, so EL, is colder than -20 degrees Celsius, you should have a potential for lightning. And if you look my graph here, my LFC, so level of free convection, is around here. That's the place where the air parcels become warmer than the environment, which allows them to rise freely, all the way up to this point, where it once again becomes colder than the environment, so this positive buoyant area is neutral. And the air parcel becomes negatively buoyant, so it starts to slow down and eventually sink. But in this point, we have EL, so equilibrium level, and we can check the temperature of that like this. So it's between -30 and 40 isolines, so it's around -35. So it should be enough to produce lightning. In this example, on the other hand, the EL level is just barely on the colder side of the -20 degree isotherm. But since it's quite dry, we might have some dry air entrainment, so dry air flowing inside of this convective cloud. And when we have dry air flowing inside, the cape profile is actually narrowing down because the cape was a produce of instability and the moisture, and if we reduce the moisture content, also cape is coming down. So this case would in real life lead into a situation where the equilibrium level is actually a little bit lower. So this is kind of on the limit whether the lightning is happening or not. There is the potential, but it's just barely there. So that is basically what you need for lightning. So the reason why you need to have at least 100 joules per kilogram of cape in this zone below the minus 20 degrees Celsius is because your updraft needs to sustain the growth of the cropel. The next thing you can see from the sounding is the potential for downbursts. Downburst forecasting is a little bit trickier, but the overall idea is that if you have dry enough and deep enough boundary layer, you can have downbursts or just heavy wind gusts. So the reason this inverted V shape is needed is that when you have dry boundary layer, the precipitation falling to this layer is starting to evaporate. And when you have evaporating, it's cooling down the layer, so the downdraft coming to this layer is cooling even more. So it's even more negatively buoyant, which means that it's accelerating more downwards. And that could lead into a downburst. The next thing is hail. According to the latest theories, hailstones are not circulating inside the cloud. That's something that we were still taught in school, but now this theory has been changed with new knowledge. So if you have a supercell storm, the hailstone is actually traveling through the cloud once and then coming out once. So what you need for hail, basically, is fat cape profile, and especially in the layer where you have supercooled water as well present there. So below minus 10 degrees Celsius, you should have fat cape profile, meaning that big portion of your cape profile should be in this layer. And here I have an example. So this cape profile is pretty fat, but it could be fatter even. So it could be extending more to the higher levels, but this should be enough to produce relatively large hailstones. If your convective cloud has big part of the cape on the warmer side, minus 10 or even above 0 isotherm, it could be producing flash flooding, so heavy precipitation. And it's because in this part of the cloud, where it's mostly consisted of water droplets, the cloud is going through a warm rain process that is allowing heavy precipitation to be the more prominent threat. For the storm to organize, you need to have shear. And there are some rule of thumbs that you can use when you are trying to forecast convective mode, so single cell, multicell, or even supercell convection. Easiest of all of these is actually the supercell convection, because what you need to have is enough deep layer shear. So when I'm saying deep layer, I can, for instance, mean 0 to 6 bulk shear that can actually be seen from the SmartMet. And here I have a value of 27.6. That is insanely large value. But when your deep layer shear is above 15, closer to 20 meters per second, you can start to forecast that the convective mode might actually be supercell convection. Then, when we are scaling down a little bit, so if our deep layer shear, so for example from 0 to 6 bulk shear, is above 10, we can start to expect multicell convection. And if the biggest part of this shear is in the layer of 0 to 3 kilometers, you can actually forecast multicell convection and more specifically squall line type of convection. And then we also have 0 to 1 kilometer bulk shear. And if this number is big enough, so from 10 to 15 meters per second, and you are forecasting also supercell convection, you can consider the potential threat for tornadoes. So when you are expecting tornadoes, the most of the shear should be closer to the ground. That allows the spinning of the air. But there are other things that you need to consider, but we are not going to go through them here. So you can find more information about all we just went through online.